Director here at SIU, and I'm going to give you guys an introduction into the PicoScope and how to make some simple measurements for automotive applications. One thing that I want to clarify before we begin is that PicoScope is a company that makes PC-based oscilloscopes. An oscilloscope is simply a tool that we use to make voltage measurements over time, whereas a voltmeter can only display instantaneous voltage readings. The terms lab scope, oscilloscope, or simply scope are all synonyms, and PicoScope is a brand that makes these measurement devices. Alright, let's begin. Here we have one of our PicoScope carts. Down below we have the actual computer tower down there itself and the physical hardware for the PicoScope, the actual scope portion itself that connects to the computer. Up top, of course, we have the monitor where we will log into the PicoScope software. It's just Pico 6 Automotive on the desktop. So you'll open that up. Up here we have the PicoScope boom, and this houses our leads, our test leads. So this is a 4-channel scope, so as you can see up here we have 4 connections, and they're all different colors to make it easy so you can tell the difference. And don't overcomplicate this. This is very simple. It's just like 4 multimeters is how I like to think of it. You have a ground and a positive test lead, your signal lead right here, and you have 4 of those, so you can make up to 4 measurements at one time, look at 4 signals at one time. This also houses the attenuator assembly up here with these switches, and we'll get more into that later. And these are held on with just a standard BNC connection. So this is how we will hook up to our vehicle. Before beginning, you will also want to grab one of our Pico kits, and these hold all the adapters that we can plug into our test leads for different measurements. The test leads that you'll use the most common, or the adapters you'll use most common, are going to be these alligator clips, just like you'd have on your standard digital multimeter. So these simply plug in to our test leads with a banana jack connection, so you just push these on. And then you can hook up to different components. You can also put back probes in here or anything else that you might need for certain measurements. The main thing I'd like to remind you is that when you're making measurements and you're hooking up the scope and making your connections, just think of this as, again, your multimeter. Lots of students get stressed out when they see all these different color wires and all these different channels, but really just think of it as a multimeter. You have your ground and your signal wire. This will be where your signal's coming out, and of course you want to hook this to a clean ground. Don't be stressed by all the wires and stuff. Just remember, this is like a fancy multimeter that can make way more measurements over time compared to your standard DVOM. Another point that I'd like to stress is that oscilloscopes measure voltage. They do not measure amperage, or at least they don't measure amperage directly. We can use an adapter like this one here. This is called a low amp current probe, and we can plug this in and then it can indirectly measure amperage. However, directly, if we're just using our test leads, we can only measure voltage as a voltage measuring device. Therefore, when you're making connections, you're going to be hooking up like you would with your DVOM in parallel, not in series like you would with an ammeter. So you might be wondering, when would I actually use an oscilloscope versus my standard voltmeter? And the answer is simple. When the voltage is changing, we use oscilloscopes, especially when the voltage is changing rapidly, such as a network communication line or certain sensor signals. We can use an oscilloscope to see those changes depicted on the screen very quickly, the changes in voltage. In those cases, we would not use a voltmeter. Generally, we use a voltmeter when we expect the voltage to be at a constant level, such as checking source voltage on the battery. Before you ever make any measurements, you always want to know 2 things. And the first thing is you want to know the maximum input rated voltage of your oscilloscope. And second, you want to have a rough idea of how much voltage you'll actually be measuring. And you want to definitely make sure that that voltage that you're measuring is less than that of the maximum input rated voltage of your oscilloscope. For example, if my oscilloscope has a maximum input voltage rating of 100 volts and I'm measuring a 150 volt signal, of course I'm going to cause some damage to my scope, and we don't want that. And that's why we have attenuators, and they actually allow us to measure voltages higher than our maximum scope's input rated voltage. The maximum input rating voltage for most of the oscilloscopes we have in the shop is 200 volts. And for most applications and most measurements, that'll be more than sufficient. However, there are certain components on the vehicle that can create large magnetic spikes from induction, such as fuel injectors and primary and secondary ignition coils. So we have to keep in mind that these spikes can sometimes go over the maximum limit of the oscilloscope, and that's why we need to remember to attenuate properly. Attenuation is simply a way to reduce the input voltage into the scope to prevent damaging it. As you can see on this oscilloscope, we have two options. We have a ×1 and a ×10 attenuation. In the ×1 option, that is simply no attenuation. For example, if I was measuring 10 volts at the oscilloscope leads, 10 volts would enter the oscilloscope itself. So ×1 is no attenuation, and ×10 is a reduction of 10 times the input voltage. For example, if I was measuring 100 volts on the leads of the oscilloscope and I was ×10 attenuating, only 10 volts would enter the oscilloscope, so that would help protect it from these higher voltages. And you can select this with these toggle switches here, and there's one for each channel. Also, these lights here help reduce some voltage spikes, so that's what those are if you were wondering. Okay, I will now give you an extremely brief introduction into the PicoScope 6 automotive software, and I'll actually have a second video where I'll go and do a much deeper dive into the software itself. But for now, we're going to keep it basic, and we're actually only going to focus on two things in this video, and that is how to set up the voltage scale and how to set up the time base. And I'll get more into that in a second. I currently have the scope set up in a demonstration mode. And PicoScope allows you to do this if you don't have a physical scope hooked up. It'll actually just give you a demo waveform. In this case, it's a crankshaft position sensor waveform that we can kind of just mess around with. And it's a really good way to practice making measurements and looking at some of the deeper functions of the scope. So I recommend trying this. So the first setting we'll take a look at and show you how to adjust is the voltage setting. And the voltage scale is on the y-axis or the vertical axis of this oscilloscope here on the left-hand side. So any y value or vertical value is corresponds to a voltage value. And we can see these blue numbers here relate to our blue waveform. Now, horizontally, this is the time base, and we can see the time down here, and we'll get into adjusting that later. But this is just a scope of voltage vertically versus time. So to adjust our voltage level, we can adjust that up here. So currently we're on an auto scale. So basically the oscilloscope is just auto ranging this for us to a value that it sees best fit. And how it ranged that is currently on a plus or minus 5 voltage scale. So above the 0 line here in the middle, we have 5 volts positive, and below we have 5 volts negative. So we're on a plus or minus 5 volt scale. Now we can go in here and manually change that. If we hit this drop-down menu for channel A, the blue channel, and we can see we have the red channel for channel B if we had a second measurement going, and green for C, but we'll focus on the blue one because that's what we're using right now. So we'll hit the drop-down, and it's currently on an auto scale. We could turn it off if we like, but of course we won't turn it off for this example. And we can see plus or minus 5 volts is selected. Now we could change this to a plus or minus 10 voltage scale. Now we can see the screen goes all the way up to 10 volts positive and negative 10 volts negative, and the waveform shrinks in amplitude. Well, the voltage level is still the same, of course, but visually it shrinks because the scale is much larger. And we can do the inverse of that if we go to a plus or minus 2 volt scale. Now we can see the waveform is actually off the screen, and that's what this red exclamation point is warning us. So that's how you change the voltage scale. And ideally you just want to set this to a point where you can see your whole waveform and it's big enough for you to point out any imperfections. Another quick trick you can do with the voltage scale is you can actually click and drag on it and move it up and down, the whole waveform up and down like so, to allow you to see the waveform better. For example, if there was another voltage reading on the screen, another waveform, you can kind of separate them and drag them around. Essentially, these measurements or these adjustments that I'm showing you today, that being the voltage scale and the time base, just allow us to see the waveform or depict it on the screen the best way we possibly can, so we can make our measurements and take the best look at the waveform we can. So next, we'll look at the time base here on the horizontal or the x-axis, and I'll show you how to adjust that. Now before I adjust it, I'm actually going to pause the waveform. We can do that by pressing this red square here. We can pause it or play it with the green triangle there, but we'll pause it. So now that the waveform's paused, we can see that we have a 5 millisecond per division time base. And I know this because each division, we can see ms here, milliseconds, each division is 5 milliseconds. So there's 5 milliseconds. Plus 5 is 10 milliseconds, and so on, and there's 10 divisions horizontally per screen, so that means we have a 50 millisecond time base for this whole screen across the whole way.
And we can adjust this by going up to the top, and this is our time base adjustment here. So it, like I said, it's set at 5 milliseconds per division. So we can change that by hitting this drop down, and we're currently on the millisecond scale here, so there's milliseconds per division. There's also seconds per division if we wanted to increase the amount of time, or if we wanted to decrease the amount of time per division, there's microseconds all the way down to nanoseconds. So let's change this to 50 milliseconds per screen and play it. So now you can see the waveform is compressed more because we're seeing more cycles of that waveform per screen. And we can actually do the opposite. So we went up in time, now let's decrease the amount of time per division, say 200 microseconds. Now we can see the waveform is spread out more. So that allows us to take a closer look at the different humps of the waveform in this case. So that's how we set our time base and our voltage scale. And again, the goal of this is to allow us to depict the waveform the best way we possibly can on the screen, depending on the measurement we're making.
Okay, to start us off, we're going to be looking at the battery voltage on this vehicle, and we're going to hook up our oscilloscope leads and check it out. So, currently I have the scope set on a plus or minus 20 volt scale. So as we can see, the blue line, it's not hooked up right now, so this is 0 volts. So we have 20 volts above the line and negative 20 volts below the line. So that's well within our range because we expect to see about 12.6 volts here. As for our time base, we are on 2 seconds per division. So you can see it's moving pretty slow. That's a pretty long time base. So per division, so as we know, there are 10 divisions per screen horizontally. We have 2 seconds per division, so that means that we have a 20-second time frame across the entire screen. Usually before taking any measurements, I like to unplug this trickle charger, as it can introduce a little bit of noise, electrical noise into our measurements. So once you have that unplugged, we can then take our leads. We have our negative and our signal positive lead. And this vehicle has a rear mounted battery behind the back seats. However, it does have a positive battery post right here that we can connect our positive lead to, and then of course we can connect the black to ground. So in this case, you always want to connect ground first. So I'm going to find a clean ground. In this case, there's a clean one right there. And then I'm going to take my signal lead and hook it up to the positive cable and take a look at the screen. We should see the voltage jump up, as it did, to 12 volts, 12.6 volts, which is our battery voltage. The last example signal that we'll take a look at is the map sensor on this vehicle. What the map sensor does is it measures the pressure inside the manifold compared to atmospheric pressure. So how I have this hooked up is the black lead is currently connected to a clean ground point, as you'd expect, and the blue signal lead is connected to the signal wire output of the map sensor. It's a 3-wire sensor. You have power and a ground to supply power to the sensor itself, and then it has a signal output to the PCM in this case, and we are back probed into that signal wire to take a look at the signal. As for the setup of the oscilloscope for measuring the map sensor, how I set it up was on a plus or minus 5 volt scale. Again, that's on the y-axis. So we have 5 volts above the line and negative 5 volts below the line. The reason why I chose 5 volt scale is because on this map sensor, it runs on 5 volts and the output signal should never be higher than 5 volts. Actually, we don't even want to see it higher than roughly 4.75 volts because that would set a DTC. And as for the time base, I'm on a 5-second per division time base, which is a relatively long time base. It'll take a long time for this to go across the entire screen. The reason I did that was just to make it easier for the video so you guys can see it better, and it'll kind of space everything out.
Okay, so here we can see our map sensor signal voltage, and first what happens is I turn the key on and we can see the voltage jump up to almost 5 volts, and that's going to read our atmospheric pressure inside the manifold once the key is on. Then the engine started and manifold vacuum increases naturally and voltage decreases with as vacuum increases. Then I rev the engine. You can see me revving the engine there, and as I rev the engine, the manifold vacuum decreases as pressure increases, and we can see that as a voltage signal.
When we're done with the oscilloscope and we might want to move it to a different area, it's important to remember to never just unplug it directly from the wall, as this can damage the computer. Always shut down the computer first, and then you can unplug it. Hopefully this video will have cleared up some of the questions you may have had about the PicoScope, and hopefully you'll feel more confident when you use it the next time around. Thanks for watching. Hopefully this helped.